went through that scenario with like the dog and the licenses, figure out if it was a function or not, look at the tables and the graphs. So right now I want you to take a look at the scenario. Felicia decides to track the snowfall. There are already 2 inches of snow on the ground from a previous storm. Felicia measures the snow from today's storm at the end of each hour. She found that exactly 1.5 inches of snow fell each hour. If it snowed at this rate for 5 hours, how much snow was on the ground at the end of each hour? So let's complete the table, and then we can write an equation. So it says like time, so 0 hours, 1 hour, 2 hours, 3 hours. So saying for 0 hours, this is already completed for us. For 0 hours, there was already 2 inches of snow. So what about for 1 hour?
Since there was already 2 inches of snow already, and 1.5 inches of snow fell each hour, that would be 3.5 inches.
3.5. Okay. So what about for 2 hours?
Following the rate that we already have, you would 5 feet.
I like the way you said that. Following the rate that we already had, so there's like a rate on every hour, it's 1.5 inches. Following the rate that we already have, then it's now 5 inches. So what about for the third hour? 6.5 inches. How did you get that?
I just added to the 1.5 inches, so each hour I just added 1.5 to 5, and got the next hour.
Good. So we have 1 more hour. Second hour to the third hour.
Mr. Grillo to the main office, please. Mr. Grillo to the main office.
Okay, so what about for the fourth hour? What do we have for the fourth hour? How many inches of snow do we have?
8.
How did we get 8?
You could see that you already have 2 hours, so you know that if that happens again, you would have 8. I'm sorry, I did that wrong. It would be 10, right?
You're right. You're right. Why did he get 8? How did he get 8? What did you do? You just added 1.5 because it's another hour. So what happens each hour? 1.5 more inches of snow. Okay, so what about for the fifth hour? 9.5. We added another 1 more hour. So we're adding 1 more hour, and we're adding another 1.5 inches of snow. Good. So how can we write an equation for this? Y equals, remember saying y equals 1.5 x plus 2. Do we agree? Where did you get the plus 2?
So basically, that's the line just said that's what she started out with in amount of time for 0 hours. So if 2 wasn't there, it would just be a proportional rate. So as it started 0 hours for 0 amount of snow that went down, and you still need to add your total snow that you started out.
Okay, I like what you said at first. You said that it's our y-intercept. So what's the y-intercept? Why is it a y-intercept?
It's when your x is 0, so you had 0 something, but yet your y.
So the x is 0, but he said we started out with 2 inches of snow already. There was already 2 inches of snow on the ground when we started. That's what Mortimer said. And it's our y-intercept. I like that you said that. So we added 2 here. So where do we get the 1.5 from? Where did she get 1.5?
You get the 1.5 from the amount of snow dropped each hour.
So each hour, we have 1.5 inches of snow. For every 1 hour, there's 1.5 inches of snow. What is that? It's a unit rate. And it's also, when we talk about lines, what do we call that? The slope. Okay. Okay, so we talked about the proportional relationship starting 0 on the 0. But this problem doesn't include 0 comma 0. How do we know the equation was y equals 1.5 x plus 2. How do we know that 0, 0 isn't a point on our line?
That's not where it's first from.
It's not, if you're just looking at the graph, that's not, we can see that it's not where it starts from. So how else can we check?
You can substitute 0 into your function you just used.
How?
You can do y equals 1.5 times 0 plus 2, and then you end up 2, so we end up 0, 2.
Yeah, so it would end up with our y would equal 2. So we know that our point, it wouldn't be 0, 0, it would be 0, 2. And that is where we start. That's what we call the initial value. We call it the y-intercept, but here it's called the initial value. It's where we're starting from.
And in a line, that is where your line crosses the y-axis. But in this scenario, think about what the word initial means. What do you think when you think of the word initial? Not like your name's initials. Like the initial
kinda.
value. How would you rewrite that? The initial value. Like how can you re-explain that?
Starting value?
Yeah, so like if I initially I was this, right? That would be like in the beginning or at the start I was that. Your initial is like the first letter of your name because that's the letter that starts your name.
Yeah.
And then value is the value. So in this scenario, while you're going to look on the graph and see where the initial value is, just the scenario, you should know that at the beginning, before any time passed, there were 2 inches on the ground. So this situation starts with an initial amount of snow of 2 inches. So that's where you're finding your initial value. It just so happens here that time is your x coordinate, and that's 0 because nothing has happened yet. So it just so happens that your initial value here is your y-intercept as well.
Okay, so from there, we're going to graph this one. So we're starting our initial value. We're starting at the 2 inches. So where x is 0, where the time is 0, and y, which is the amount of snow, is 2 inches. We're going to start there. From there, how are we moving? Over 1. Why over 1 like in this scenario? Because what changed? The time, like 1 hour, and then what? And then we're rising 1.5 inches, or what's happening in this scenario? What does 1.5 mean here? Yeah, 1.5 inches of snow. So for 1 hour, we have 1.5 inches of snow. So that's like the horizontal change, how we're moving left and right. And then that's the vertical change, how we're moving up and down. So it's up and down. Left and right, 1.5. Moving up and down, 1.5, and then over 1. So this graph shows the rate of change. So that's why I really like the way you said that earlier, Mortimer. You said it's the rate at which the snow is falling. So the ratio of change between y and x values is called the rate of change. From point to point, the y values change by 1.5. We just said that. From point to point, we go up 1.5. And then the x values change by 1. So we're going to go to the right 1 because x, we know x moves left and right, and we know y moves up and down. So the rate of change is what? What's the rate of change here? 1.5. Good. Because we're moving. Why? Because we're moving where?
Because your snow is growing compared to your time is your x. So basically, your y is always changing compared to your x is basically measuring how long or basically it's always going to say true.
So it's the change in y over like the change in x, right? So it's the rate at which y is changing, and then the rate at which x is changing. So we know that x is changing. It's from 1 hour
What's another word for that? Change in y over change in x.
Is it the constant portion?
Well, actually, at its root, it is because the constant of proportionality is also the unit rate. But like in terms of this scenario, when the change,
Slope.
yeah, it's really the slope of this scenario, right? But think about what a rate of change means. If you saw this situation, like, hey, there were 2 inches of snow on the ground, and every hour an inch and a half fell, you're not going to say, what's the slope of the snow? Because you're just talking about a scenario, right? What's the rate of change? What's the rate at which your snow is falling? And you could say an inch and a half every hour. So your rate is 1.5 or 1.5. So we're really talking about the same thing, just in different contexts. If you're looking at a graph, it's the steepness. If you're talking about this function or this scenario, it's its rate of change. How is it changing? It's nice that they end up being the same thing when we graph it.
Can functions have different initial values and rates of change? Functions have different initial values.
I'm like, what do you mean?
Like, can a function, can different functions have different initial values and rates of change? Or do they all have the same initial value? And they all have the same rate of change?
Can you think of an example of something that would be a function that has a different initial value than another one? Use the snow example. Okay, so there's 2 inches of snow on the ground, and then every hour, an inch and a half more snow falls. Okay, that's a function. Its initial value is 2. Its rate of change is 1.5. Let's say next week it's going to rain. Can you give me a scenario that would have a different initial value and rate of change? What would it be? Can you give me a different example? Do we always have 2 inches of rain on the ground? What could you have?
0.
Okay, let's say you have no inches of rain. You have no rain on the ground. And then what's going to happen every hour?
Every hour you can grow your rain, maybe.
Well, how would you explain that? Every hour,
More rain is poured on.
how much rain is going to fall?
2 inches.
Okay, 2 inches. Does that have a different rate of change than our snow example?
Yes.
Yes. So you just answered your question. Can they have different initial values and rates of change?
So what, in that scenario, what was the initial value? 0. And what was the rate of change?
2.
Perfect.
Okay, so in your groups, I want you to take a look at this. Dora opened a savings account and deposited $50. So right away she went to the bank, she went to the savings account and deposited $50. When she gets her paycheck each week, she wants to put $25 more into her savings account. Every week she's going to get her paycheck, put $25 into the savings account. So figure out what the initial value of the situation is, and how do you know, and then figure out what the rate of change for this situation is, and how to define that. Okay, so in your groups, I want you to figure this out and talk about it, okay?
Should I freeze it now? So we're just going through the examples next.
Yeah.